Good morning. Hi, I'm Tony Lee. We'll be talking today about a brief history of router architecture. Mostly this is a tour down memory lane. I will be dumping on people who messed up on the architecture. That's everybody. Nobody is innocent here, so everybody is going to get a fair share. I'm not going to name names. I'm not out to actually hurt anybody. Just trying to point out all the mistakes we made and all of the things we learned. This is also based on my non-ECC protected neurons. I have no documentation of all of this because at the time it was all under NDA and all of that stuff has been burned. So all the errors are mine. So when we started off, routers looked like computers. There was a bus and a CPU hanging off of it and NIC cards stuck in the bus. And this really sucked. Packets came in one NIC, went across the bus, up through the CPU, into memory. Then we do a lookup, rewrite the output of the packet, shove it back across the bus, and back out a NIC. Every packet is traversing the bus twice. So you have to have a lot of bus bandwidth for this. Guess what? Nobody did. It sucked. Buses and CPUs are centralized resources in this architecture, and they scale linearly. You want to build a bigger box? Well, you've got to beef up the bus and the CPU. And because you're stroking the bus twice, you've got to double the amount of the bus. What's worse is as you change the bus speed, you have to change all of the NICs in the bus. All of those interconnects are going to be cost you depending on just how fast the bus is. This does not scale at all. So this really just sucked. And it did not last for long. Now, unfortunately, architectural change is hard and risky. And when you don't know what you're doing, you don't make radical changes. So if you don't want to make a radical change and one bus is not working, how about we add a bus? And we need some more compute power. So cheap compute power comes in the form of an ALU. In this case, it was a digital signal processor, and that got stuck on and a faster bus with new NIC cards. But this doesn't change the problem. It gives you more bandwidth, that's true, and a few more cycles per packet, but it doesn't really fundamentally scale things. Okay? Small constant improvement, sure, but it's not an architectural change. Then we went off and said, well, this IP address lookup is painful. What happens if we make this a little bit faster? And we stuck an FPGA onto the ALU. And that let us do hardware lookups for the first time. And that was better, but it didn't help that much, surprisingly. Well, okay, we can do packet forwarding on hardware, and that's good, but we're going to abandon that. And we're going to do something else. But the IP address lookup turns out to not be the only bottleneck. Adding lookup hardware only saved a little bit of the CPU time, and there was still lots of congestion just from data handling. The real issue is centralized bandwidth. We need distributed bandwidth and processing. If you don't distribute it, you're going to get stuck. And then the web came along. The carriers bought up the NSFnet regionals. The real money started to flow. We had to get serious and not play around. Everybody else wanted to build a router. ASICs became serious, and people started doing interesting things. We had lots of crazy ideas at that point. We went first to a scheduled crossbar. Here we take inputs, seen on the bottom, and send packets Actually, we divide them up into cells and then send them to the outputs. And we schedule it so that we figure out who's going to send when. This looks great in theory, but the fact is that internet traffic is horribly irregular. It's even fractal in nature, and it's never going to be as uniform as you like. So the scheduling never works out quite nicely. Worse, you can't always drain your inputs, so you end up with head-of-line blocking. We had systems that had these problems. Throughput really suffers when that happens. What you really need to do this is the inputs need a queue per output, and you need to be able to schedule a cross matrix of inputs versus outputs. And if you do that, that becomes a really big problem, and it doesn't scale. It just sucks. Okay, here's a crazy one I can't even draw. What if we arrange our router in a torus? Well, theoretically, that looks great. It's consistent, but what happens? Well, it's non-uniform bandwidth. And now our bandwidth can take very different paths across the torus, and you can end up having congestion at certain points around the torus. If you take out a card, you break the fabric, and you end up with even less uniform fabric, so you cause more bandwidth issues. Our bandwidth needs to be distributed, and it needs to be uniform. And this is actually a key point. So we went off and we tried something else. What happens if we have a distributed cell memory and a full mesh of interconnectivity? Okay, this has gotten some nice properties. Our bandwidth now is uniform. Any packet gets divided up into cells, sprayed across all of the various NICs, and then there's even uniform bandwidth going back out. But we've created another problem by doing this. What happens if you lose a NIC? If you hot swap a card out, all the packets in the system, throughout the system, are lost. You've lost cells from everything. You can't reassemble anything, so basically, it's restart the forwarding plane. That's not good. We also have a problem because the bandwidth of the system is a fixed multiple of the bandwidth of the card. If I want to build a bigger system, I now have to build different cards that have more bandwidth. That's still not scalable. How do we get to something scalable? From there, we went off and we tried something very, very simple. Well, what happens if we take all of this and dump it into one giant memory? Okay, it's uniform. Hot swapping NICs doesn't cause a problem. Is this better? Well, it's better in some senses. We have uniformity. Things are well distributed. We don't have queuing problems. But memory bandwidth is somewhat limited. We can only build memories that are so big. And in doing so, we end up with a problem that we still can't scale. So this sucks too. Really need to do something very, very different. Well, again, architectural change is hard and expensive, and it took us a long time, but we finally stumbled on listening to something invented a long time ago by the telephone network. Charles Clough, who is a researcher in switching theory, came up with a topology that gave us something interesting. Now, he started off doing this with telephone calls, of course, but we can take the same basic ideas and apply it and build a Clough network. In this, you see inputs on the left, cell switches peppered throughout the fabric, and outputs on the right. Why is this good? Well, this is a nice architecture because it's very redundant. If you lose anything, there are alternatives. Okay? And Everything is uniform. You can always get from input to output. Okay? Now, in practice, our input cards are the same as our output cards. So if you fold this thing in half, you actually get a simple network that looks like this. This is called a folded flow network. And if you turn it sideways, and you're from Arista, you are going to call this the leaf spine architecture. Everybody uses this all the time. Okay? This sucks a lot less. Okay? Bandwidth is distributed, it's uniform, it's redundant, but our scalability is still very limited. To avoid problems, our inputs need a queue per output. That helps, but that means that we can only have a fixed number of outputs when we design the system to begin with. That's a limitation on scalability. Our cell addressing turns out to be finite. We have to have address bits in the cell, and that means that our fabric can only be so big. And we have to fix this when we start designing the fabric hardware. So we have to make a decision up front, very early on, about how big our fabric is going to be. And unfortunately, the cell fabric turns out to be proprietary. That's a real problem. That ends up with creating all sorts of issues because we can't change out the cell fabric. Technology upgrades seem to be very difficult to roll in. Okay? If you've designed silicon around a fabric and you have new silicon that's going to go, say, 10 times faster, how does it interface to older silicon? How does it do so smoothly? And lots of folks have tried this, and we've never been able to make it work. The problem ends up being primarily that we end up with lock-in. If you do this, you end up with vendor lock-in. You buy one part of the fabric, and you end up using the same chipset, and end up using the same software vendor or hardware vendor, and you're stuck. You end up using the same architecture and the same system for the entire lifetime of the system. That can be a serious problem. Some people are working right now to try to get this opened, and they're trying to standardize on a particular chipset, but that just shifts the problem from being a pure hardware vendor problem to an ASIC vendor problem. And giving the ASIC vendor a lock-in or the system software vendor a lock-in is not an advantage. You're just moving the problem around. You're not solving it. What can you do? Well, we'd like to propose the same idea, but let's use packet switches instead. Let's use Ethernet between the switches. And now this does look very much like a leaf spine or super spine architecture. But underneath it, it's really a closed topology because we're using Ethernet and we've got industry standard links. We've got industry standard switches. We can easily do incremental upgrades. We've got very good vendor independence. We can do all of this with standard protocols. So we've got pretty good interoperability. We're packet, not cell-based, so we are going to need a little bit of extra bandwidth. Things are not going to be as smooth simply because the atomic level that we're operating at is now going to be 1500 bytes, not 53 or 64. The nice part is that our fabric scales. We can add more stages of switches, or we can add more width to our switches. Either one works. You can do both depending on what you need for a particular architecture. This is the big win. This is where I think we're headed in terms of architecture. Now, there's some software issues that we need to work on. What we really need to do is take that architecture and we want to make it look like a single router. It's got to work on the control and the management planes. We need some work to do this, We're working on this currently in the IETF. We're trying to improve abstractions in the IGP. We'd like to make our supernode look like a single router, and we've got some protocol changes to do that. We also have to make our supernode look like a single router from a management plane, and we've got a proxy solution in the works that'll take us to doing that. So this is where I think we're headed. We have to figure out ways to scale. Scaling has been the #1 problem we've always had. Thank you very much.
Thank you, Tony. It was an excellent talk. We do have some questions for you in the Q&A tab. If you out there watching have any questions for Tony, please put them in the tab now. This is your chance, and you can get to answer him. So, Tony, would you prefer to read the questions yourself or have me read them to you?
You can read them, Steve.
All right. So Chris Woodfield asks, for the benefit of those who haven't been in the business as long as we have, around what time periods did these various architectures come into production use?
So the original bus architecture started with the IMP, and of course that started around 1969 in networking usage. Since then, we started seeing multiple buses, I think around 1990. And then crossbar started showing up around 1996. And Boss Network started showing up around 2003.
Okay. And a question from Matt Bitek. So here we are with almost 2 decades of class networks and half a decade of packet class networks with data centers and backbones. Thoughts on what the next iteration will be? Supernode is just a wrapper and isn't fundamentally different.
So I expect class networks to continue to grow for quite some time, mostly because we haven't found anything the least bit better. We've been playing with lots of things for a long time and haven't seen any improvements on the horizon.
And Dan Megorian is asking, how does the supernode approach get around limitations of the constituent routers?
Well, it gets around redundancy for the obvious ways. It gets around having to build giant single control planes because it's now really distributed and loosely coupled, which are really major improvements. Those are the major benefits right there.
Okay. Does anybody else have any questions while we still have Tony? Here's one. Blake Willis is asking, do you think Ethernet's MAC header is required inside of an Ethernet-based router fabric?
Well, clearly it's not necessary. We really don't need all of those bits identifying the node. But on the other hand, we very, very, very much want to stay standardized. So that should never change.
And Tony Tauber asks, what are the trade-offs between multi-box clause and as many are doing and single box clause as you propose?
I'm not proposing a single box clause. I'm suggesting that we always build things with multiple boxes in a clause internally, and then wrap software around it to make it look like a single box so that we can scale. That's the important part. We need the hierarchy.
Eric Osborne is asking what IETF work is ongoing. Are you referring to draft Lee hierarchical ISIS?
I've referred to several drafts that I'm talking about. One of them is dynamic flooding. That improves flooding inside of dense networks. Another one is ISIS area proxy. This improves the area mechanism in ISIS so that it collapses entire areas and makes them look like a single node. And yes, the hierarchical ISIS draft is also there for additional scale.
Okay, last chance. Any questions? All right, then. That's it. Thank you very much, Tony. That was a fascinating look at where we've been and where we're going. Appreciate you coming here to join us today.